Episode 4 of our lovely little calculus adventure today. We'll begin with Theodore, who is currently enjoying a nice slumber. Hopefully you all don't slumber as we learn some more calculus. So we're going to talk about the second derivative test here. And specifically, we're going to start by looking at a couple examples. Let's look at a cubic function. Let's look at some weird function like this. And let's look at x to the fourth. This last one is the only one I'm going to give you the equation to, because I really want to specify that this last one is not a parabola. Okay. I was checking to see if October was still at the window. She's not. So we have a local minimum right here and right here. We have a local maximum right here and right here. And so the first derivative test we talked about already. Increasing to decreasing is local max. Decreasing to increasing is local min. Here we're saying, well, what is this? What does the second derivative tell us about these things? So let's look at the second derivative, and then that's going to kind of give us some motivation for what we think the second derivative test might be. And then we'll actually talk about the second derivative test and we'll compare. So on this first one, we have a critical point at this green point at the top left. And to the left, it's concave down. And to the right, it's concave down. Right? Specifically, everywhere around the green point kind of looks like a parabola. A downwards parabola. We have a local max, and it's concave down. Second derivative has to do with concavity. Well, with this blue point on this first graph, everywhere around the blue point is concave up. So it's a local min, and it's concave up. And we could draw any amount of, right? We could draw as many polynomials as we wanted, and notice that all of these local mins, it's concave up. All of the local maxes are concave down. So for polynomials, it really is going to work this way for a lot of polynomials. But here, right, we have a local max. But in this case, right, to the left, it's concave up. To the right, it's concave up. We got that more like the smiley face. So it's concave up everywhere. So what's going on? What's the difference? This is going to be one of those exceptions. In the past, we had exceptions when the function was piecewise, when it wasn't continuous. Here, it's going to have to do something with continuity and being defined as well. And over here in this last one, we're going to have another exception. This is a local minimum, but it's going to turn out that the second derivative here is equal to 0. So it's not concave up or concave down here at the point itself. It's concave up on both sides, but at the point itself, it's neither. So this is what we would like the second derivative to tell us, the second derivative test. And the second two are some exceptions. And that'll all be incorporated in this theorem, the second derivative test. So let's talk about it. What do we need to assume? Those exceptions, just like in the first video here, just show us examples of, well, this doesn't work always unless we assume certain things about our function. So suppose that this first derivative of a function at a point is equal to 0. So that's the first part right here. We're not talking about just any critical point for the second derivative test. We're talking about specifically a critical point where the first derivative is equal to 0. So you can't use the first derivative test or the second derivative test right here. You can only use the first derivative test. First derivative test does work here. Second derivative test does not work here because the second derivative test only works when the first derivative exists. It does not work on all critical points. All right. Suppose the first derivative is 0 and f double prime is continuous around C. So it's continuous on an open interval containing C. Then one of three things is going to happen. If the second derivative is positive, so concave up, if it's concave up at that point, then f has a local minimum. And again, what does that look like? That looks like this situation. Concave up, horizontal tangent line, that's going to be a local min. If the second derivative is negative here, if it's concave down, what do you think is going to happen? Going to have a local max. Right? Concave down with a horizontal tangent line is a local max. If the second derivative equals 0, well, then we can't use the test. There's no conclusion. So this is the way that this test is always phrased in every textbook I've ever looked at. But really what it should say is that you can't even use the test here. We should be assuming that here. We should assume that the first derivative equals 0 and the second derivative doesn't equal 0, but it's fine for them to formulate it this one. So that's this last case. So even though there is a local minimum, the second derivative test doesn't apply. The second derivative test doesn't tell us anything about this third example because the second derivative is equal to 0. So the second derivative doesn't give us the concavity at that point. All right. So that's what's going on here. So there's some pros and cons to the first derivative test and the second derivative test. Second derivative test can a lot of times be easier. There's less to plug in, but you do need the second derivative and it doesn't apply to as many situations. So can be easier, less to plug in, but doesn't work all the time. And I already forgot the other con. you have to take the second derivative. All right, there we go. Let's use it. Example 3. Goldfish day. Find and classify all local extrema for f of x equals x to the 5th minus 5x cubed. So how do we find them? Look at critical points. That's true whether using the first derivative test or the second derivative test. If we want local extrema or absolute extrema as well, we need critical points. First derivative test applies to any critical point. Second derivative test, well, any critical point where the function is continuous. Second derivative test only applies to critical points where the derivative equals 0. So f prime of x equals 5x to the 4th minus 15x squared. When is that equal to 0? First off, let me comment that it is defined everywhere. Critical points are when it equals 0 and when it is undefined, but it is indeed defined everywhere. So how do we solve this? This is a quartic function, a 4th degree polynomial. And before you freak out and say, I don't know the quartic formula, which exists for certain subclasses of quartic functions, but you don't need any quartic formula or anything. Let's factor. Let's take the greatest common factor out. We can take out a 5, and we can take out an x squared. And that leaves us with x squared minus 3. So this first thing is true when x is equal to 0, and the second thing is true when x squared minus 3 equals 0, when x squared equals 3, when x is plus or minus the square root of 3. Can be a good idea to go off to the side to do calculations if you want to save a little bit of space. Okay, so we have critical points at 0, comma, plug this in to the original function. Original function gives you our y values. Critical points at 0, comma 0. At negative square root of 3, comma something. I'm gonna use a calculator on this one. F of x equals x to the 5th minus 5x cubed. Whoa, that's a capital X right there. I don't know if it likes capital X's. It did not like capital X's. F evaluated at the square root of 3. And again, this is an odd function, so if I add a negative here, it should just flip the sign of my answer, and it does. About 10.392. You could find an exact answer if you needed, which would be a good idea, but it'd be a little messy. And positive root 3, negative 10.392. All right. These are our critical points. We'll classify them with the second derivative test. So we actually don't need any chart for the second derivative test. Why? Because the second derivative test only matters what the concavity is at that specific point. So that's why second derivative tests can be a little nicer. So we have this, that's great. The second derivative is continuous everywhere as well for our function. It is a quartic polynomial, so polynomials are continuous. So all we have to do to use the second derivative test is test what is the concavity at each of these critical points. So to test the concavity, we need the second derivative. Take the derivative of the first derivative to get the second derivative. Power rule here gives us 20x cubed minus 30x. And you could factor this or not factor this as you like. If we were looking for inflection points, points of inflection, we would want to factor this. So we can solve when it equals 0, but we don't need to for the first derivative test. Sorry, for the second derivative test. All we have to do for the second derivative test is say, what are the signs at these critical points? So when x is 0, when x is 0, the second derivative is 0. No conclusion. Inconclusive. Second derivative test, inconclusive. Second derivative test doesn't tell us anything here. We got scammed. Jason, you asked us to use the second derivative test, but it doesn't even work. That's one of the downsides of the second derivative test. It doesn't always work. But in this case, right, it was much quicker to just calculate the second derivative and plug things in. We'll have to use the first derivative test on this one. But the other ones were fine. I don't want to calculate this all out, but second derivative going to be 20x cubed minus 30x. And the second derivative at the square root of 3 is a very big positive number. So that's going to be concave up. Going to be a local min. Negative square root of 3. What's the second derivative? Well, it's a negative number. That's going to be concave up. Going to be a local max. This guy, though, we have to use the first derivative test for. So there's a critical point at 0. The other critical points are at root 3 and negative root 3. So we only need to look at this interval and this interval. Let's look at the sign of f prime and whether it's increasing or decreasing. And we don't have to test every interval because we already used the second derivative test to look at these guys. We just have to look at intervals around 0. So -1 and +1 work. If you look at square root of 3, it's about 1.7. So the first derivative at -1. This is the first derivative when it's -1. That's going to be a positive times a negative. Remember that logic that we did before. Positive times a negative is a negative. It's negative or decreasing in this interval. The first derivative at +1, when we plug in +1, again, it's positive times a negative. Oh. That's also negative, so it's decreasing. So the first derivative test, second derivative test told us it was inconclusive. First derivative test told us that it wasn't any local extrema. So no local extremum. At x equals 0. So let's write up our answer. Local min of something when x is the square root of 3. About -10.392. That's not going to fit. And we found that there's a local max of +10.392 at x equals, that's not going to fit either, at x equals -√3. And those are our only local extrema. And if the problem asks you to give an exact answer, then you wouldn't have these approximations like this. But for this one, it doesn't matter. And that's how we can kind of tie it all together. Let's graph this and consider. So this is our original function. At -square root of 3, we have a local max, just like we said. At 0, there's a critical point, but there's no local extrema. At +1 square root of 3, we have a local minimum, just like we said. If we plot the derivative, if we plot the second derivative, notice the second derivative, white is the second derivative. Notice the second derivative is very negative down here. It's concave down. Notice the second derivative is 0 here. And at this local extremum, notice the second derivative is very, very big. It's concave up. The blue graph. The white tells us the concavity of the blue. That's how it ties together. Good luck to you. That's all the concepts. So I have 2 more videos, but this is all the concepts for the whole homework assignment. So you should be able to do the whole homework assignment now. But the next 2 videos are just doing more stuff to give you guys more resources, more types of problems, more information, more context. So the next 2 are optional. Go ahead and enjoy because it's math and calculus is fun, right?